When we observe the motion of planets and stars in the night sky, Earth serves for us as a frame of reference to describe the instantaneous positions of the celestial bodies. However, our planet also performs a complicated motion. Earth rotates about its axis once every 24 hours, while it revolves around the Sun with a varying velocity along an elliptical path. Furthermore, Earth possesses an axis of rotation that is not perpendicular to the plane of its elliptical trajectory, and has an angle of inclination that undergoes a precession with a period of 26,000 years. As a result, the description of the apparent motion of the celestial bodies is also complicated in this rotating and revolving frame of reference. It was therefore a great challenge for the astronomers in ancient times to construct a cosmological model providing a satisfactory description of celestial motion. Philolaus, a follower of the Pythagorean school in Greece, developed an astronomical system with the planet Earth rotating about its axis, while it revolves around a central fire distinct from the Sun, which also orbits the central fire. Thus the central fire is at the center of Philolaus' cosmos. The Sun and the planets move in perfect circles at constant angular velocity, executing the ideal form of motion. As already mentioned in the discussion on Aristotelian physics, the expectation of the ancient Greek astronomers was that celestial bodies must perform a uniform circular motion. In the Pythagorean cosmology, the motion of the stars and planets along circular paths representing a perfect geometric shape indicated the divine nature of the celestial objects. Aristotle also noticed that a counter-Earth was also introduced by Pythagoreans in order to bring the total number of the planets and the Sun orbiting the central fire up to the perfect number 10. Another Greek philosopher and astronomer, Heraclides Pontius, modified Philolaus' system by creating a geocentric worldview with the assumption that Earth is at the center of the universe. In his cosmology, our planet is at rest, whereas the Moon, the Sun and the outer planets revolve around Earth. Only the inner planets, that is Mercury and Venus, revolve around the Sun. Nevertheless, all the planets and the Sun has circular orbits and they move at constant speed along their paths. The most mature version of the geocentric cosmology is called Ptolemaic system after Ptolemy, an Alexandrian astronomer and mathematician. His model became a predominant description of the universe from antiquity and remained unchallenged till the beginning of Renaissance. The geocentric model assumes that the Earth is at rest and the center of the universe, and the Sun, the Moon and all the planets and stars revolve around the Earth. Although the Sun and the Moon move in circular orbits around the Earth, planets perform a composite motion in the geocentric model. They revolve around small circles, called epicycles, whose center C move along bigger circles, known as deferents. The center O of the deferents is called eccentric and it is at a given distance from the Earth. A planet performs uniform circular motion along its epicycle, and the same time the midpoints of the same epicycle moves along its deferent at a constant speed. This combined motion could explain the observations that the trajectories of planets appear loops in the sky where they have a retrograde motion. However, the geocentric model became more complicated with the improvement of the observational data, since in its original form it could not predict the observed size of the planet's retrograde loops. Ptolemy introduced the equant point E placed directly opposite to the Earth from the eccentric of each planet. He supposed that the center of the epicycle moves at a constant angular velocity with respect to the equant, which would produce a uniform circular motion. The improvement using the concept of equants was a deviation from the Pythagorean idea of perfect motion in the celestial spheres, and Nicholas Copernicus saw it as an aesthetic shortcoming which indicated the internal contradictions in the Ptolemaic system. The combination of different types of circular motion based on epicycles, deferents and equants became complicated, and it seemed to be a more straightforward way to interpret the planetary motion in a system with the Sun at the center. In his heliocentric cosmological model, Copernicus claimed that the planets including the Earth revolve around the Sun located at the center of the universe. Furthermore, each planet rotates around its axis, while orbiting the Sun. Then we can describe the motion of planets in a frame of reference attached to the Sun, and we can choose any coordinate system with the origin at the center of the Sun and the axes directed towards the fixed stars in the sky. Giordano Bruno claimed that Copernicus' heliocentric hypothesis was more than a mere mathematical formalism interpreting planetary motion. His model disproved not only Ptolemy's model but also the Aristotelian picture of the cosmos. According to Bruno, the heliocentric worldview completely rejects the fundamental idea of the peripatetic physics stating that the elements had the natural place at the center of the cosmos in the sublunary region. Bruno denied the existence of the celestial and sublunar spheres, indicating that the same laws of physics must be applied throughout the cosmos. Furthermore, Bruno also claimed that the universe is infinite and populated an infinite number of solar systems. This hypothesis goes far beyond the principle of heliocentric worldview, stating that there is no center in the universe at all. Tycho Brahe, a Danish astronomer, also admired Copernicus' work and tried to confirm his theory by studying the trajectories of objects in the sky. He performed the most precise observation of celestial motion before the invention of the telescope by applying a brass azimuthal quadrant seen in the figure. However, his observations did not prove the existence of the annual parallax of stars, which should be the result of Earth's motion around the Sun. Instead of abandoning the idea of the Earth located at the center of the cosmos, he constructed a geo-heliocentric system combining the immovable Earth with Copernicus' heliocentric geometry. In his cosmology, the Sun revolves around the Earth, whereas the inner planets orbit the Sun, providing a picture similar to Heraclides' astronomical model. His assistant, Johannes Kepler, already accepted the Copernican system. When he analyzed Brahe's observational data on Mars, Kepler applied the mathematical tools developed by Ptolemy to explain the observed motion in the heliocentric worldview. By assuming that the Sun does not move while Mars orbits the Sun, he tried to fit the parameters describing the geometric model with the observational data as much as possible. As a result, he discovered the laws of planetary motion, breaking with the heritage of the Pythagorean cosmology, where planetary motion was explained as a composition of uniform circular motions. Let us study the three laws of planetary motion discovered by Kepler. These laws describe the motion of the celestial objects around the Sun with the point mass approximation, where the diameter of any orbiting planet is much smaller than the size of its orbit. Kepler's first law is called the law of orbits, and states that planets move in elliptical orbits with the Sun at one of the two foci. In other words, the planets in the solar system perform an elliptic motion while orbiting the Sun. As we have already seen in the discussion on elliptic motion of a point mass in kinematics, the elliptic orbit has a few parameters describing its basic properties. The shape of an ellipse is given by its major semi-axis A and minor semi-axis B, whereas its position is fixed by the locations of its foci F1 and F2. The eccentricity E of the elliptic orbit is also used to describe the shape of the orbit, which can be written as the square of 1 minus the ratio of B squared to A squared. The instantaneous position of the planet is described by the position vector pointing from either the focal point F1 or the focal point F2 to the position of the planet moving along the ellipse. If the Sun is at the focal point F1, then the reference point is F1. If the Sun is at the focal point F2, then we chose F2 as a reference point. The magnitude of the position vector gives the instantaneous distance of the planet from the Sun. In kinematics, we also derive the polar equation describing the instantaneous position of a point mass on an ellipse. If theta is the polar angle measured between the major axis of the ellipse and the position vector of the point mass, then the polar equation states that the distance r of the point mass from the reference point is given by the semi-major axis a times 1 minus the square of the eccentricity e, divided by 1 minus or plus e times the cosine of the polar angle theta. In other words, the instantaneous distance of the planet from the Sun is uniquely determined by the polar angle describing the direction of the position of the planet with respect to the major axis of its elliptical orbit. The sign in the polar equation is determined by the choice of the reference point. If the Sun is at the focal point F1, then we take the minus sign. If the Sun is at the focal point F2, then the plus sign is used in the denominator. Kepler's second law is known as the law of equal areas, and states that the position or the radius vector pointing from the Sun to any planet sweeps out equal areas during equal intervals of time. This law can be illustrated as follows. The position vector of the planet at a given time t1, and the position vector at the time t1 plus delta t determine the area delta A swept out by the moving position vector during the time interval delta t. Similarly, the position vector at the time t2 pointing to another position in the orbit of the planet and the position vector at the time t2 plus delta t also determine the area delta A swept out by the moving position vector during the time interval delta t. Since the time interval delta t is the same in both cases, the area swept out by the position vector are the same. As a result, it is not the instantaneous velocity v of the planet that is constant along its elliptic orbit but its areal velocity. When we studied the elliptic motion of a point mass with a constant areal velocity defined by the derivative of the area A with respect to the time t, we show that the areal velocity of the moving body can be written as 1/2 times the cross product of its position vector r and its velocity v. Kepler's law states that the vector of the areal velocity is constant. The first law also tells us that the orbital motion of the planets is a planar motion, and the position vector of the planet and its velocity, that is the tangent to the elliptic orbit at the instantaneous position of the planet, remain in the plane of the motion. Then the direction of the aerial velocity of the planet is perpendicular to the plane of the motion, and the second law states that its magnitude is constant during the periodic motion of the planet. We also derive the magnitude of the aerial velocity in kinematics, and we can write that 1/2 times the square of the distance r of the planet from the Sun, times the derivative of its polar angle theta with respect to the time t is constant. It follows therefore that the instantaneous velocity of the planet has a maximum at the perihelion of its orbit, that is at the point nearest to the Sun of the planet in the path of the orbiting celestial body. Similarly, the planet has the minimum velocity at the aphelion, that is at the point farthest to the Sun of the planet in the path of the orbiting celestial body. Kepler's third law is called the law of periods, and states that the ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of the semi-major axes of the elliptic orbits. If the semi-major axis and the period of the elliptic orbit of a given planet are denoted by A1 and T1 respectively, and A2 and T2 are the semi-major axis and the period of orbit of another planet in the solar system, we can write that the ratio of T1 squared to T2 squared is equal to the ratio of the cube of A1 to the cube of A2. In general, we can state that the square of the period Ti of the planet with the index I divided by the cube of the semi-major axis Ai of the orbit of the given planet is constant. In other words, the squares of the orbital periods of the planets are directly proportional to the cubes of the semi-major axes of their elliptic orbits, and the third law simply tells us that the proportionality constant is the same for each planet. Now we will give an overview of the fundamental parameters describing the planetary orbits in the solar system. This table shows some of these parameters for the 9 planets revolving around the Sun. The table contains the semi-major axis of the planetary orbit, the orbital period, the orbital eccentricity, and the inclination to the ecliptic for each planet. If we compare the values of the semi-major axes measured in 10 to 8 kilometers, we can see that the average distances of the outer planets are 40 to 60 times greater than those for the inner planets. We can also see big differences in the orbital periods, which are only few months in the case of Mercury and Venus, and hundreds of years for Neptune and Pluto. In order to check the validity of Kepler's third law for these data, let us compute the proportionality constant appearing in the law, that is the ratio of the cube of the major semi-axis of the orbit to the square of the period for any planet. For Mercury, this fraction is equal to the cube of 0.591 times 10 to 8 kilometers, divided the square of 0.241 year. Since the cube of 10 to 8 kilometers divided by the square of 1 year can be written as about 1.004 times 10 to 18 cubic meter per second squared, we obtain about 3.335 times 10 to 18 cubic meter per second squared. If we compute the same fraction for all the other planets in the solar system, then the result will be the same, indicating it is a constant for any celestial object revolving around the Sun, as stated in the third law. By considering the data series for orbital eccentricity, we can conclude that Mercury and Pluto have the most eccentric elliptical orbits. However, the orbits all the planets in the solar system have small eccentricities, and the planets revolve around the Sun in almost circular orbits. In the last column of the table, we can see the inclination angles of the orbits to the ecliptic, that is to the orbital plane of the Earth. These data show that the majority of planets have elliptic orbits with moderate inclinations to the ecliptic within few degrees. Only the orbits of Mercury and Pluto have the inclination angles of 7 and 17 degrees respectively. As an illustration, we show the relative size and inclinations of the orbits of the gas giants and Pluto in this figure. The trajectories of the rocky planets in the inner belt of the solar system are omitted from the figure, since the average diameters of their orbits are negligible to those of Neptune and Pluto. We also see that Pluto revolves around the Sun in a highly inclined orbit, whereas the inclination angles of the orbital planes are relatively small for other planets. When we studied circular motion in dynamics, we introduced the concepts of central motion and central force. We talk about the central motion of a point mass when its acceleration has an arbitrary magnitude but always points towards or away from a fixed point. Any force producing central motion is called central force. Due to the second law of motion, we can also state that a central force acting on a body always points towards or away from a fixed point. It follows from Kepler's laws that planetary motion is a central motion, and the force acting on any celestial object orbiting the Sun always points towards the Sun. In order to prove this statement, we formulate a general theorem. This theorem states that if a point mass performs central motion, then its trajectory is a plane curve or a line in a special case, and its aerial velocity is constant. Conversely, if the trajectory of a moving point mass is a plane curve and its aerial velocity is constant, then the point mass performs central motion. Since Kepler's first law tells us that planets orbit in ellipses which are plane curves, and the second law states that the areal velocity of any planets is constant, then it follows from the converse of the theorem that the planetary motion is central motion. Now we prove this theorem and its converse by applying geometric methods. Let us suppose that the point mass at the instantaneous position A0 performs central motion with respect to a fixed point O. The point mass leaving the point A0 covers some distance during a small time interval delta t, and arrives at the point A1. Then the moving point mass leaves the point A1 and arrives at the point A2 after covering some distance during the time interval delta t, and so on. Since the time interval delta t is small, we can approximate the path of the motion with a series of the displacement vectors A0 A1, A1 A2, A2 A3 and so on. Each displacement vector can also be approximated by the product of the velocity of the point mass measured at the tail of the position vector and in the time interval delta t. As a result, the length of each displacement vector is proportional to the magnitude of the velocity measured at the tail of the position vector. We can construct the motion of the point-like body as follows. The body arriving at the point A1 from the point A0 would reach the point B1 after the time interval delta t, if it had no acceleration pointing towards the center O. Therefore the magnitudes of the displacement vectors A0 A1 and A1 B1 are the same. However, the change in the velocity directed towards the point O is proportional to the length of the vector A1 C1, and its vector sum with the displacement vector A1 B1 gives the true displacement A1 A2. Similarly, the body leaving the point A2 would reach the point B2 after the time interval delta t if it had no acceleration pointing toward the center O. Then the vector sum of the change of velocity proportional to the vector A2 C2 and the displacement A2 B2 gives the true displacement A2 A3, and so on. It follows from this construction that the point mass cannot leave the plane defined by the points O, A0 and A1. Since the displacement vectors A0 A1 and A1 B1 lie on the same line, the vector A1 B1 is in the plane of the triangle OA0 A1. Similarly, the vector A1 C1 lying on the line OA1 is also in this plane. Then the displacement vector A1 A2, which is the sum of the vectors A1 B1 and A1 C1, lies in the plane defined by the points O, A0 and A1. This can also be proved for the displacement vector A2 A3, and so on. As a result, the series of the displacement vectors A0 A1, A1 A2, A2 A3 and so on remains in one plane, that is the path of a point-like body performing a central motion is a plane curve. If we compare the triangles OA1 A2 and OA2 B2, we can see that they have the same area since their bases A1 A2 and A2 B2 have the same length and their heights drawn from the point O are the same. However, the triangles OA2 B2 and OA2 A3 have also the same area since the vector B2 A3 is parallel with the line OA2 due to the parallelogram law, and the heights of the two triangles drawn from the points B2 and A3 from the common base OA2 are equal. Therefore the triangles OA1 A2 and OA2 A3 have the same area, indicating that the area swept out by a point mass during the time interval delta t are the same in a central motion. This proves the theorem. In order to prove the converse of the theorem, we need to demonstrate that the acceleration of the point mass at the point A2 points towards the point O, supposing that the areas of the triangles OA1 A2 and OA2 A3 are equal. If we construct the triangle OA2 B2 such that its side A2 B2 is equal to the length of the vector A1 A2, then the areas of the triangles OA1 A2 and OA2 B2 are equal. It follows from the supposition that the triangles OA2 B2 and OA2 A3 have also the same area. As a result, the heights drawn form the points B2 and A3 to the common base OA2 of the triangles OA2 B2 and OA2 A3 must be equal to each other, that is the displacement B2 A3 must be parallel with the line OA2. Since the displacement vector B2 A3 is proportional to the acceleration at the point A2, the acceleration must also parallel with the line OA2, and must point toward the center O. This proves the converse of the theorem. In the discussion about elliptic motion, we also demonstrated that the motion is central motion if the areal velocity of the point-like body traveling along an ellipse is constant. We used a polar coordinate system attached to any of the focal points from which the position vector R sweeps out equal areas in equal times. The radial coordinate is given by the magnitude of the position vector, and the azimuthal angle phi is measured between the position vector and the x-axis. Then the instantaneous acceleration of the moving point mass could be decomposed in radial and azimuthal directions. The magnitude of the radial component is given by the radial coordinate r double dot minus r times the azimuthal angle phi dot, where the dot denotes the derivative with respect to the time t. Similarly, the magnitude of the azimuthal component can be written as r times phi double dot, plus 2 times r dot times phi dot. If we write the magnitude of the areal velocity of a planet performing elliptic motion in polar coordinates, then we have 1 over 2 times r squared times phi dot. Now we assume that the areal velocity of the planet is constant. By multiplying this equation by 2 and taking its derivative with respect to the time t, we obtain the equation stating that 2 times r dot times phi dot, plus r squared times phi double dot is equal to 0. However, we can identify the left-hand side of the equation as the magnitude of the azimuthal component of the acceleration, which is 0 now. As a result, the planet has an acceleration only in the radial direction, that is towards or away from the focal point of its orbit. Therefore, the planet moving along the ellipse with constant areal velocity performs a central motion, where the sun at the focal point is the center of the motion.